Hello, everybody. Welcome back. Today we're going to continue discussing magnetic field. And we have two goals for today. We want to talk about the magnetic field of currents, which is what we can measure with compasses, and most of you have actually seen that already. The rest of you will see it this afternoon in lab. And so we want to see what we can predict theoretically about that. And we also want to talk about magnets. So how do magnets make magnetic fields? So that is our agenda for today. So where did we get to last time? Where did the chat go here? So last time we discussed the Biot-Savart law, which is the equation for calculating the magnetic field of a single moving charged particle, because we found that magnetic fields were due to moving charged particles. And that equation is important enough that you actually do have to memorize it. And it looks like this. So the magnetic field of a single charge is a constant, which is called mu0 over 4 pi. So this is the Greek mu sub 0 over 4 pi. It depends on the charge. It depends on the velocity of the particle. And it's the cross product of the velocity times and r hat, where r is the vector to the observation location, and over r squared. You do need to memorize this. And it's very important to note that this is r hat, not r. A lot of the mistakes people make in calculating magnetic fields are because they actually use r, which has a magnitude much greater than 1 there, instead of r hat. And note that like the electric field of a single charge, it falls off like 1 over r squared. So if you're twice as far away, the magnetic field you observe will be only a quarter as large. So what we were doing is working toward being able to predict the magnetic field of a current, a lot of moving charges in a wire. And the way we're doing that is basically we want to be able to count the number of moving charges in a little segment of wire, and then we can add it up just the way we added up the electric field of distributed charges. So that's the goal. And we've gotten as far as defining electron current. We use the symbol lowercase I, and that turned out to, so this is the number of electrons per second entering a section of conductor, and it ended up depending on the density of mobile electrons in the material, which depends on the material, and that's what makes, that's one of the things that makes some materials better conductors than others, times the cross-sectional area of the wire times the average drift speed. I don't know. Zopf is kind of an interesting thing to say. No, that's a constant. You don't need to memorize constants. The value of mu0 over 4 pi is exactly 1 times 10 to the negative 7 Tesla, which is the unit of magnetic field, meters squared per coulomb per second, I think. And Coulomb meter per second. Coulomb meter per second. Sorry, Coulomb meter per second. And so you don't have to memorize constants. You may, but and then we also talked about conventional. I like move. Conventional current. Which has units of coulombs per second, is just the absolute value of the charge of the mobile charge times the electron current. And so it's Q N A V. You don't have to memorize these equations, but you do need to know what the symbols mean, and what the units of these things are. So you need to know this is the density in electrons per cubic meter. This is the cross-sectional area. And this is the average drift speed. Now, now there's kind of an interesting thing about this relation, the Biot-Savart relation, predicting the magnetic field from a moving charge, and it's this. So so if you have you make a charged tape like you did in electrostatics experiments by ripping it off another piece of tape, and so you've got this charged tape hanging from a table, and you're sitting there. You don't see a magnetic field due to the tape because the tape isn't moving, right? But if Marco decides to run past your table, from his point of view, the tape is moving relative to him, and so he should actually detect a magnetic field. And so this is the first situation we've seen where the existence of a field, and by implication a force, although we haven't talked about magnetic forces yet, actually depends on your frame of reference. And so motion relative to a charge, you'll see a magnetic field, but if you're sitting still relative to a charge, you won't. And so that's actually kind of an interesting thing, and we'll see later when we get to talking about magnetic forces that some of these ideas are the ideas that actually led Einstein to develop the theory of special relativity. So we'll see how this plays out. But for now, we note that it's very interesting that this depends on your frame of reference. So what V do you use in this equation then? Well, you use the velocity that in your frame of reference. So if you're sitting still, the tape is not moving, and so the magnetic field is 0. If Marco's running, then the tape has a velocity of -7 meters per second in the plus x direction to him, and so he uses that velocity in calculating magnetic field. But this is an interesting issue. Okay, so today we want to be able to calculate the magnetic field of a current, lots of charges moving in a wire, and we want to look at two interesting cases. One is just a long straight wire, and then we're going to look at a loop of wire, or a coil, which is many loops of wire with current running through it, and see what we see. So we're going to use exactly the same procedure that we used when we were calculating the electric field of distributed charges. So magnetic field of currents. So we're gonna divide our current source, the wire or whatever it is, into little pieces, into segments. We'll and approximate each as a moving charge. Then we're going to find the little bit of magnetic field delta B due to one segment. And we're going to add it all up and check our answer. So that's a very familiar procedure. The only difference is that we're calculating magnetic field instead of electric field. One question though is are we going to work with would we work with conventional current or electron current? The electrons are what's really moving in these currents. So what do we use? Well, it turns out that it actually doesn't matter in many situations which we use. And here's one way of thinking about it. So here's a battery, and you know a battery's got a little bump on the end at the positive end and the negative end. And suppose we use a battery, we put a capacitor, we connect a capacitor to a circuit with a battery. So we put a wire from that end, from the negative end of the battery to one plate of the capacitor, and a wire from the positive plate to the other end of the capacitor. Now, what's really happening here in our circuit, unless we're using very unusual material, is that what we've got electrons moving through the wire, and electrons do what you'd think they do. They come off the negative plate of the negative end of the battery, the end of the battery marked negative, and so they have these velocities here, and so they flow onto this plate of the capacitor, and we start to pile up negative charge here. And of course, those negative charges are making a field in the wire over here. So the electrons here want to move away. And so they move toward the battery, and that leaves a deficiency of electrons on that plate of the capacitor, and so we get the capacitor charged with negative on one side and positive on the other side. So this is electron current. Well, what if we thought about conventional current? So what if we had exactly the same circuit here? So here's our capacitor. Here's our wires coming off of the battery. And this is the negative end, and that's the positive end. Well, if the charges we have are mobile positive charges, then they would come out of the positive end of the battery and flow the other direction. And so we'd have positive charges going that way and flowing onto this plate of the capacitor. Now these are absent. It doesn't do to think of these positive charges as protons. These are fictitious positive charges, because Ben Franklin guessed wrong. And all these positive charges would make an electric field, here in the wire, and so these mobile positive charges would want to move in the direction of the field, and so they'd be moving onto the negative end of the battery. And again, that would leave a deficiency of positive charges here. And it turns out the capacitor would charge exactly the same way. We can't see a difference. What about magnetic fields? Would the magnetic fields made by the circuit be different? Well, so here's a little section of wire with negative charges moving to the right. So let's look at an observation location here above the wire. So here is R hat. That's pointing from this little piece of wire to our observation location. And so what direction of magnetic field would we predict at that location if the charges in the wire are negative and they're moving to the right? Well, we use our right hand, so we'll point our fingers in the direction of V. And then we have to rotate our wrists so that we can fold our fingers toward our hat. That means our thumb sticks out toward us. And now we have to take into account the Q in the bios of our law. So V cross R hat is out of the page, but these are moving negative charges. And so the magnetic field would be into the page at this location. And down here on the other side of the wire, we'd have R hat going that way. So V cross R hat, our thumb points into the page, but these are electrons, so the magnetic field is actually going to be out of the page. Okay, so that's what we'd predict for electron current. What would we predict for conventional current? Well, conventional current, we've got positive charge, these imaginary positive charges, and they are moving to the left. And so let's figure out what we'd predict, in the same locations for magnetic field. So in the first location up here, we've got R hat. So we have V cross R hat is into the page, and these are positive charges, so we don't have to do anything. So we predict B into the page. And down here at the bottom, to this observation location, V cross R hat is out of the page, Q is positive, so we're good. So it turns out that we get the same prediction for electron current or conventional current. And so we can't use the magnetic. So one consequence is we can't use the magnetic field to tell us whether the moving charges are positive or negative. We have to do a different experiment. And the second is that if we're just trying to predict the magnetic field made by a current carrying wire, it's simpler to work with conventional current because we don't have to worry about the sign of the charges and we don't have to worry about flipping the fields, so that we will typically work with conventional currents. So we want so our equations for magnetic field of current carrying wires will work with conventional current. The units of conventional current, remember that conventional current is the absolute value of the charge in a V. It has units of coulombs per second, and that's called an ampere, or sometimes just it's abbreviated with a capital A, or sometimes just an amp for short. And that's what you'll read on meters when you use meters to measure how much current there is. Okay, so now we're ready to predict the magnetic field made by a current in a wire. We're going to divide the current into pieces, approximate each piece as a moving point charge, get an expression for the magnetic field contributed by one piece, add them up and check. So here's our wire, and what we're going to do is take one little piece of the wire with, we're going to say it has a length delta L, so that's the length of our piece here. And inside this wire, there are some number of imaginary positive charges moving, let's say they're moving to the right. So the magnetic field made at some observation location, so if here's an observation location and here's our vector r, the magnetic field at some observation location would just be delta B, the magnetic field due to this little piece, is equal to the number of moving charges in this segment times the magnetic field of one charge, which is mu0/4 pi q v cross r hat over r squared. Okay, so we need to find out this number, just the number of moving charges we've got. So the number of moving charges is just equal to the density of charges times the volume of the segment. So this is electrons for mobile charges per cubic meter. And this is just the volume of our little cylinder, which is the cross-sectional area times the length. So that's area times length. So that's A times delta L. So our delta B now reduces to the number of moving charges in A delta L times mu0/4 pi q, where now q is a plus E because we're calling these positive charges, qv cross r hat over r squared. And that's due to this one segment of the wire. And now we can play a little game here with vectors and directions. We can write the speed of the moving charge, which is in the direction the charges are moving, and the magnitude is the average drift speed. So we can just factor it into the magnitude of V times the direction that the charges are moving. And we can actually decide that we're going to make delta L a vector instead of V. So delta L is just going to be a vector that has the length of the segment and is in the direction of the charges. So we can make delta L up here. We'll actually make it into a vector whose length is just the length of the segments by doing the following thing. We can say in our equation here, we've got a delta L and a V. And so we can say instead that V delta L times V goes to the magnitude of delta L times V hat times the magnitude of V, which goes to the vector delta L times the speed. And I'll write it without the decoration here, or I'll just write it as the magnitude of V. And having done that, we can just rearrange this a little bit. So we basically are moving the magnitude, we're moving the magnitude of V out here and the magnitude of delta L into there. And so now we get delta B is equal to N A V. And we can also move the Q because that's a constant. So Q N A V mu 0 over 4 pi delta L cross R hat over R squared. And this is just the conventional current. So delta B is going to be equal to mu 0 over 4 pi, the conventional current times delta L cross R hat over R squared for one segment. And so now all we have to do is write that out and add it up. Let's see what we would do if we were doing it numerically, though. So what would this look like if we did it using VPython? Okay, so here we have a current carrying wire. The current is running from left to right, and we've divided it up into segments. And so this little magenta arrow is now our delta L, and for this very first segment, and it's pointing in the direction of conventional current flow. So this is the direction that these imaginary positive charges are flowing. And the red arrow is R, so our observation location is actually right here at the left end of the wire for now. And there's a little teeny cyan arrow there, which is hard to see, which is the contribution of that particular segment of the wire to the magnetic field there. So we have delta L cross R hat. See if you can figure out which way the and this is off to the side of the wire. So let's see what happens when we step through just adding up the contribution of each segment. Okay, so the field is getting bigger and bigger and bigger and bigger as we add the contribution of each segment of the wire. And as we get farther away, the contributions get very small. And when we get to the end, we've added up the contribution of each segment. And so that is the net magnetic field at that observation location due to every segment in the wire. And now we can do it for a different observation location. We can add up the contribution of each segment. And now we'll speed it up because it's getting sort of boring. And as we take observation locations around the wire, we can see that we're getting this pattern of magnetic field that we saw for a single moving positive charge. Okay, and now we can add a whole bunch of other observation locations. And since there are moving charges everywhere in the wire, we find that all along this wire, unless we're really near an end, the magnetic field has the same magnitude. And as we move farther away, it gets smaller. Okay, so that's basically what our prediction is going to be. We do it. That's what we get when we do it numerically. And so all we need to do is now do this using calculus if we can. And I don't want to spend a lot of time on this derivation, because you've seen things like it before. I'll show you basically how we set it up, but I think you get the basic idea here. So one of our goals in doing this is to figure out what the distance dependence is. So we'd like to find distance dependence. As we move away from the wire, we saw the magnetic field got smaller, but we didn't see how much smaller it got. Now, some of you actually have already tried to measure this in lab. You put a wire over a compass, and then you moved it farther away, and you measured the magnetic field by looking at the compass deflection, and then you tried to figure out the distance to fit it, to get a distance dependence. So let's see what we'd actually predict here. So let's put our wire vertically here, and let's say conventional current, so our imaginary positive charges are moving upward, and so the wire is in the plus y direction, and what we want is an observation location in the xz plane, so somewhere along the x-axis. So here's our observation location right there. So this is plus y, that's plus x, and so what we need to do is just pick a piece of the wire, just like we took a piece of the rod, a charged rod, to represent as. So we want to take a piece of the wire, so a little segment here, and so its length is delta L. In this case, it's along the y-axis, so we can call this delta y here. So here's our piece of wire. And we need a vector r from the source to the observation location. And so we'll call this distance x here. So this location is x, 0, 0, and the center of this is 0, y, 0. So r is going to be x, 0, 0 minus 0, y, 0. So that's going to give us x, negative y, 0. And the magnitude of r is going to be the square root of x squared plus minus y squared plus 0 squared. And so r hat is x, negative y, 0 divided by the square root of x squared plus y squared, the quantity. Yeah, so we'll write it this way, x squared plus y squared to the 1/2. And so our expression for delta B is going to be equal to mu 0 over 4 pi. I delta y cross r hat over r squared. And so we're going to get a mu 0 over 4 pi I delta y. We have 0, 1, 0. So delta y, the vector is the length of delta y times the vector 0, 1, 0, because that's so. Cross r hat is x negative y 0 over x squared plus y squared to the 1/2. And this is over r squared, so we have an x squared plus y squared, so that's our delta b. Well, the direction, let's do direction and magnitude separately. So the direction is given by 0, 1, 0 cross x negative y 0. And that comes out to, if you work out all the terms, 0, 0, minus x, or that cross product comes out to x times 0, 0, negative 1. So we know that the direction is going to be in the negative z direction. Okay. And so now all we need to worry about is magnitude. And so we end up with the magnitude of b is equal to mu 0 over 4 pi. Let's pull the constants out. We have the conventional current. We have an I times the x from this cross product. And now our delta y turns into a dy, and so we have an integral of dy over x squared plus y squared to the 3/2. And our integration limits, well, we need integration limits, so we don't have any infinite wires in our supply closet. And so if the length of the wire is L, then our integration limits are going to be from minus L over 2 to L over 2. So we're going from minus L over 2 to L over 2. And when we get all done with that, at the end of the day, we get the magnetic field, the magnitude of the magnetic field. Notice this is not a vector, is mu 0 over 4 pi L times I over x times no, it's not. So the reason it's not x squared plus y squared to the 1/2 is that we had to take into account r hat as well. So this combines to give us the 3/2. And this cross product here, which we worked out, combined to give us that. And so we pull the x out because x is a constant and y is our integration variable, and we end up with this. So that's where it came from. But thank you for asking. So we have x squared plus L over 2 squared to the 1/2, and the direction is minus z, which we got from the cross product. So we can draw our little delta b in the minus z direction. And so a key thing to note here is that every piece of the wire gives us a delta b in the same direction. It doesn't have the same magnitude, but it is in the same direction. And so that meant that that made our integral much easier. And again, there's nothing, this is a situation that has cylindrical symmetry where cylindrical coordinates make more sense. So we can write this as the magnetic field, the magnitude of the magnetic field of a long wire, of a wire, a current carrying wire, is mu0/4pi, the length of the wire, the conventional current in the wire, and we'll just call the distance from the wire r because it could be in the x direction or the z direction or something like that. So r squared plus quantity L/2 squared square root of that. So that's an exact answer. And if you're close to the wire, or wire is long, then we have this same thing where r is much less than L. And if r is less than L, then in this sum, we can say r is negligible compared to L/2, especially because r squared is going to be even much less than L/2 squared. And so we can get an approximate equation that'll actually tell us something about distance dependence. That turns out to be, if we actually work that out, it comes out to be 2I divided by R. And so we see that if L is greater than distance from the wire, if you're close to the wire, it's a long wire, it looks like we get a 1/R distance dependence. Which is what we'd expect for an ideal long wire. So not 1/R squared, but 1/R. And remember that we found the electric field of a uniformly charged long rod actually fell off like 1/R if we were close to the rod. So this is really a geometric factor combining with this 1/R squared dependence to give us that. Now notice this is not a vector. So notice, and you don't have to memorize this, it will be on equation sheets, but notice that it is not a vector. And notice that we certainly can't use an r hat to get the direction, because the direction of r hat and the direction of the magnetic field are utterly different. So we have to use the right-hand rule to get the direction, and we do that by just taking some segment of the wire, and in this case we luck out because all segments contribute B in the same direction. So we use a segment of the wire and we get the direction. Let's see how we think about this. Okay, so the question is the equation for the observation for an observation location only on the midline of the wire, with the wire, which is what we calculated here, or is it for any observation location? Well, although technically we've only calculated this for a single observation location. So remember that when we did this numerical calculation with this finite wire, we got pretty much the same results everywhere we look. Now, we didn't look right at the end of the wire. Okay, so we were looking at locations near, I'd say not very near the ends of the wire, right? So again, there really is almost no difference. Not really a visible difference in the pattern we're seeing in the middle of the wire and the pattern one step over or two steps over here. They all look the same. So basically the answer is we can use this as long as we're not near the ends of the wire. And as long as we're reasonably close to the wire. The farther out we go, then the more the wire starts looking like a moving point particle, right? And so as you get farther and farther away and the wire starts to look smaller and smaller and more like a point, then it's going to start looking like 1 over r squared. But let me say again, these approximate equations are your friend. Not only are they a whole lot easier to calculate with correctly, but they actually give you some intuition about how the field should fall off with distance. Okay, so let's see if we can actually figure out a distance. Is that the question I want, or do I have one that actually has? Okay, so here are the answers. 1 is plus x, 2 is minus x. Or actually, let's do it this way. North, 1 is north, 2 is south, 3 is east, 4 is west, 5 is into page, and 6 is out of page. Okay, we'll do it that way. So the question is, we have a wire lying on top of a compass, and we don't know which direction the conventional current's going, but we can deduce the direction of the magnetic field due to the current in the wire here. No, we do have this plus x minus x. Okay, so let's establish a coordinate system. So this is y, that's x, and z is out. So by looking at the compass, what direction was the, yeah. So mostly you said minus x. And that's correct. But let's review because it looks like, so never mind this. That was a red herring. Maybe that confused you. So we have the Earth's magnetic field, we know is pointing like that. We know the compass is pointing in the direction of the net magnetic field. So indeed, the magnetic field made by the current had to be to the west. Okay, given that, what's the direction of the conventional, spelled wrong? What's the direction of the current, the conventional current in the wire? Now they're really, okay, well, let's just see what you say. Okay, so let's, given that you know the magnetic field has to be to the west. Now remember, our coordinate system is is y, x, z out. So think about this as meaning that what's the direction of motion of these imaginary positive charges that are making this magnetic field? Okay, let's stop and talk about this, because this is what you said, and that's sort of a mess. So here's the wire on top of the compass. So here's our wire going like that. Is it possible for charged particles in the wire to be going that way? Or that way? So here's a charged particle in this wire, and presumably somewhere not shown is a battery. So let's put a battery. Here's a battery. We don't know which end is which, but there's a battery in this circuit making the current. So if a charged particle is moving, say, to the left, it's just going to hit the edge of the wire, right? It's not going to fall out of the wire. So particles, moving charges in this wire have to be moving. There's only two ways they can be going. They could be going up, or they could be going down, right? So there's really only two possible directions for conventional current in this wire. Given that, and given, so you know that magnetic field under the wire points that way. And you know that conventional current either goes up or down. So there are really only two possibilities. So given those things, let's try again. What's the direction of what's the direction of the conventional current in the wire, where we've got where our coordinate system is shown. Okay, let's try this again. Now, to get this right, you have to think about where the observation location actually is, because you're going to use the right-hand rule. So the key to getting this right is thinking about where the observation location actually is. Okay, so that's what you said. And let's see how to think about this. Okay, so that's close to evenly divided. So actually, let's go back to our Python program with the hand. Okay, so we had in the coordinate system we were using in that question, we had y up, x to the right, and z out, so like we are now. So here's one of these positive charges. And we know that, so now the question is, where's the observation location? Well, the wire is on top of the compass, so therefore the observation location has to be behind the wire. So that would put our observation location on the minus z axis in this coordinate system, right? So let's just try some things. So if we choose plus y and minus z, that says there are only really two things to try, so it's trial and error. We know minus z, that's the direction of where the observation location is. So let's just see what happens. We orient our fingers, we use our right hand, point our fingers in the direction of the motion of this imaginary positive charge. We actually don't have to rotate our wrist. So we've aligned our fingers with V, they're already aligned with V. We have to rotate our wrist so that we can fold our fingers toward our hat. Well, it's actually already okay. So we fold our fingers toward our hat, and now our thumb sticks out in the minus x direction. And that actually was the direction of the magnetic field. So that looks like it works, right? If the charges are moving up, then we get the right direction. Now let's just check to see what would happen if the charges were moving down. So again, our observation location is in minus z, but this time we're going to say the charges are moving in the minus y direction. So now we have to turn our hand. We don't really have to rotate our wrist because we're already in a position to fold our fingers toward our hat. And now our thumb sticks out in the plus z direction. And so that would give a magnetic field toward the east, not the west, in that coordinate system, and that doesn't work. Okay, the first one was the one that worked. So in fact, conventional current has to be flowing up to make a magnetic field in that direction underneath the wire. Now, the next thing I want to talk about is a loop of current. And so, here's a wire there's a loop. Now, this is a simplified diagram, so obviously, unless this is a superconductor under unusual circumstances, you're not going to get current flowing in this loop unless there are wires connecting it to a battery. But let's say the wires connecting it to a battery are going, say, up or down in such a way, both of them, that they're very close together and they contribute almost nothing to a magnetic field here. So we're really only interested in the magnetic field made by the loop itself. And we have current. So we look down the x-axis, we have current. This is in the loop is in the YZ plane. Our observation location here is on the x-axis. And current is flowing toward us, in the plus Z at the top of the loop and minus Z in the bottom of the loop. So current is flowing counterclockwise in the loop. Now we can do this analytically, but it's actually more interesting to do it numerically. Analytically, we can get an answer on the axis, but it's more interesting to do it numerically. So what we're going to do is just, here's our little segment of the loop. So you can almost see, there's a DL. Okay, good. Now we can see our DL. So that's going that way. That's the way current's flowing. And now as we step around this loop, we see that we're getting all these little dBs here. So each little piece contributes a magnetic field in a slightly different direction. And we've gone all the way around, and we see that it looks like the Y and Z components are actually going to cancel out, and all we're going to get is a non-zero X component on the axis. Sorry, that's the Z axis. So we've got a non-zero Z component. Let's look at some other locations. So here it's not quite symmetric. So when we add these up, we're going to get a total net magnetic field that way. Here, pretty asymmetric, so the net field is kind of like that. On the, what we consider the perpendicular axis, interestingly, we only get contributions in the plus or minus z. And we add up all the contributions in lots of places. And so does that pattern of, this is the magnetic field of this current carrying loop, but does it look familiar to you? Yes, it is. It's a dipole, isn't it? And so a current loop is a magnetic dipole. It produces a pattern of field that's very characteristic of a dipole. Notice that the field on the axis of the loop points all in the same direction, and the field on the perpendicular axis points in the other direction and is half as big. So it's exactly the that's exactly the field of a dipole. And of course, this is a slice through the field, right? So if we do this in, so that's in one plane, but if we do it in another plane, we get, you know, the same pattern. So this is a three-dimensional pattern of field. So it looks like a magnetic, a current carrying loop is a magnetic dipole. And of course you would get, if you made two loops instead of one, you'd get a field twice as big, et cetera, et cetera. So we'd be going on that way. I'm not going to go through the derivation, which is in the book. But so but of course, and as you might expect, your integration variable when you do that integral is actually theta. So on the axis of the loop, the magnetic field, the magnitude again of a single loop, the magnetic field of a single loop comes out to be mu 0 over 4 pi, 2 pi r squared I over r squared plus z squared, so on the z-axis, where r is the radius and I is the conventional current. And at the center, so there's some special cases here. So at the center of the loop, so here's our current flowing this way. The center of the loop, z is 0. And so we actually get mu 0 over 4 pi, 2 pi I divided by the radius of the loop. And it's very far away. Oh, this is, sorry, to the 3/2. I missed something there. Very far away, we get a mu 0 over 4 pi, 2 pi r squared I over z cubed, which is exactly the dipole dependence. And if we had 3 loops, we'd get 3 times as much. So the magnetic field, so these are results. So this is approximate. And this is the exact. And again, the approximate equation is your friend. And of course, so this is on the axis, on the perpendicular axis, the magnetic field of the loop. Perpendicular axis is going to be exactly the same, except it's going to be half as big as B on the axis. So remember that when we talked about electric dipoles, so we talked about the dipole moment. So we had the electric field on the axis was 1 over 4 pi epsilon 0 2 qs over r cubed, and this thing we called the dipole moment, which had the unfortunate symbol P, the electric. Well, for a magnetic dipole, the magnetic field on the axis is mu 0 over 4 pi 2 pi r squared I over z cubed. And so this whole thing is the magnetic dipole moment. And unfortunately, the symbol is mu, so the Greek lowercase mu, not mu sub 0, but just mu. And so the magnetic dipole moment is equal to the area, cross-sectional area of the loop times the current. Now, something that's possibly a little that's interesting here is that there's another thing that's a magnetic dipole besides a current loop, and it's just a bar magnet. So a bar magnet is a magnetic dipole. And the end we call north has magnetic field coming out of it. And the end we call south as, I know, right? We just need another alphabet. We should be using, Sanskrit or something, Devanagari. We just don't have enough alphabet letters in our alphabets. So the what we call the north pole of the magnet has magnetic field pointing out of it, and the south pole has magnetic field pointing into it. And so the question is, how does a bar magnet manage to make a dipole field? Are there current loops in a bar magnet? Why is a bar magnet a dipole? And the answer is that there actually are current loops inside a bar magnet at the atomic level. There's 2 kinds of currents at the atomic level. There can be an electron orbiting a nucleus, So this is this is basically translational. If an electron has translational angular momentum, right? And if you think of an electron as a little ball of charge, it can also spin as it on its axis. So this is due to its rotational angular momentum. And so an atom, a single electron, is in fact a magnet all by itself because of its spinning around on its axis. And an atom can be a magnet due to the orbiting of the electrons, but it turns out, and the spin, but it turns out that what has to happen is that you need to have, you need an unpaired electron. And you need all this, the magnetic dipole moments of all these electrons to line up the same way. So you need all the little magnetic dipole moments must line up. And there aren't that many substances where this works out. First of all, you have to have unpaired electrons. And second, magnets don't really want to all point the same direction. So if we take two magnets here, so the north end likes to stick to the south end. So if I try to put them together, south end to south end and north end to north end, they actually are repelling each other here. They don't want to do that. What they want to do is stick together lined like that. So they want to be like that. And so that's hard to do. And that's actually why only certain substances, usually transition metals or rare earths that tend to have unpaired electrons and have weird energetic structures, end up being bar magnets. Okay, we can't go into that more right now because we are out of time. We might talk about it slightly more at the beginning of next time. What's the takeaway? What's the most important takeaway message for today? When we say magnet, it doesn't matter whether we're talking about cylinders or rectangles. We're talking about an object that has magnetic, that is a permanent magnet, and it can be any shape, because a permanent magnet, unless you're talking, I mean, a permanent magnet basically is a dipole, and if you cut a magnet in half, you just get two little magnets, two little dipoles, and it doesn't make any difference whether it's a bar or a cylinder or anything else. It's a piece of magnetic stuff. Okay, so in your opinion, what's the most important takeaway message? Now, we haven't talked about forces yet. We've only talked about fields. Magnetic dipoles are really, really important. So a loop being a dipole really is interesting. Yeah. All right, we'll practice with this. Well, we could talk about electron current all we want, but what there is what's out there in the world is conventional current. I think just because it's algebraically easier not to have to worry about negative signs and flipping directions.